Hello everyone. In this video, we are going to discuss how we can get the PIV or the peak inverse voltage of any rectifier. So peak inverse voltage refers to the maximum voltage a diode in a rectifier circuit must withstand during the reverse bias condition. When the diode is blocking the current, that is when it is operating in reverse bias mode. Now, if this diode is exposed to a voltage higher than its PIV rating, it will be destroyed or it will fail due to breakdown, allowing a current flow in the reverse direction, which obviously will have damaged the diode. So let's talk about the PIV value for a half wave rectifier. So consider our half wave rectifier that consists of one diode. So in the reverse mode or reverse bias mode, you'll find that a positive, the negative half cycle or the negative voltage signal will appear across the diode, but of course in an opposite direction. So this means this voltage is, this AC signal is going to be blocked. So when it is blocked, there is going to be a PIV or a peak inverse voltage across the diode. Now, if the positive of the signal is here and the negative of the signal is there, and what appears across the the terminal of the transformer is Vm, or the secondary peak voltage is Vm. So what is going to be our PIV? So we apply KVL. So when we apply KVL, we will find that we will have Vm, okay, minus what is across here is V naught, or the DC voltage output across the load resistor. So minus V naught, so obviously minus PIV, and this is equal to 0. But remember, since there is no signal passing through the diode, then there is no voltage that is going to appear across the load resistor, and this is only and only true for a half wave rectifier because it is having only one diode operating. So that means V naught is going to be 0. So if V naught is equal to 0, Vm minus PIV is equal to 0, and PIV is equal to Vm. So that means the peak inverse voltage for a half wave rectifier must always be greater than or equal to Vm. Let's talk about PIV for a full wave rectifier. So let's talk about a full wave rectifier, and we take an example of a bridge rectifier. So this is a bridge. For a bridge rectifier, if it has the diodes connected in such a way that this and that are in a forward operating mode, or they are forward biased, then this and that are reverse biased. So a signal which will come will pass through diode, this one, let me call it D1, D2, D3, and D4. So when it goes through D1, it will appear across the load resistor, and there will be a voltage drop V0, and through D2 and back to the source. So what is happening? So that means D1, if we consider a real silicon diode, and the voltage drop across the diode is Vf, therefore Vm, okay, Vm is more positive compared to D1, so Vm will force current through D1, then across the resistor node, and across D2 and back to the source. So Vm minus Vf, okay, across here, minus V naught minus Vf across here will equal to 0. So V naught will therefore equal to Vm minus 2Vf, and that is equation 1. So equation 2, we are going to consider when these diodes have broken down. So those that are in reverse bias or in a reverse bias condition are going to have a PIV. So also here we have a PIV. So this PIV here, remember this coming was positive and negative. So if we consider this loop, we are going to consider this loop. So if we consider that loop, we will have IV, okay, because if we follow that direction, then there is a voltage rise. So PIV minus V naught, which is a voltage drop, then minus Vf is equal to 0. Actually, is also okay, yes. So V naught, let us see. Yes. So V naught will equal to PIV minus Vf. And so this is equation 2. So from 1 and 2, from 1 and 2, obviously Vm minus 2 Vf will equal to PIV minus Vf, and our PIV must equal to Vm minus Vf. So that means PIV of these diodes must always be greater than or equal to Vm minus Vf. So, but if Vf is so small, then we can say that PIV should always be greater than or equal to Vm, and that is for a full wave bridge rectifier. Now let's talk about a center tap rectifier. So a center tap, if we consider that being a transformer and that is the load resistor, then we are talking about diodes. Those are diodes. So this is the load resistor. This is diode D1. This is D2. And this is plus, this is minus, this is plus, this is minus. And across here you have Vm. Across here you have Vm. Now, in forward conduction mode or in forward bias mode, D1 is conducting, and therefore you'll have V naught appearing across RL. So if we consider this rule, okay, apply KVL here. So if you apply KVL here, and if this has a forward voltage of Vf, then you'll see that Vm minus Vf minus V naught will equal to 0, okay? And then your V naught will equal to Vm minus Vf. So we are going to also talk about if now this current coming, when it reaches here, it divides. Some goes through this and other current goes through this diode. But because it is in reverse bias, then it will not conduct. And what is going to appear there is instead going to be PIV. So PIV, you have plus. So what is this going to be? This is coming, okay, and is going to be like that. So meaning, if we apply also KVL, you see that your Vm here, okay, your Vm here Instead, now here we'll have a plus V naught, okay, then minus PIV, this is equal to 0. So what is V naught? V naught will be PIV minus VM. So from star and 2 and equation 2, you will see that PIV minus VM will equal to VM minus VF. So PIV will equal to 2VM minus VF. And therefore, for center tap full wave rectifier, PIV will always be greater than or equal to Vm, whereby Vm is the maximum or the peak secondary voltage of the transformer minus Vf. So if Vf is negligible, then PIV must be greater than or equal to Vm.